In this video, we're going to cover whether to use ideal gas law, the PV equals nRT, or the combined gas law, PV over NT equals PV over NT, in some of these problems that are going to come up in your lectures, exams, and homework. Let's take a look at this problem here. A sample of oxygen gas occupies 2.50 liters at a pressure of 1.20 atm and a temperature of 27 degrees. So I'm going to write that in a list format. So I have my volume, which is 2.50 liters, pressure 1.20 atm, and I have my temperature at 27 degrees Celsius. The gas is compressed to a volume of 1.80. So volume has been diminished. So that I have a second volume, and that second volume is 1.80 liters at a constant pressure. If it's a constant pressure, the pressure is still 1.20 atm. The question asks, what is the new temperature of the gas in Kelvin? So here's my second temperature, and I put a question mark. So the question again is, should we use the combined gas law or should we use the ideal gas law? If you look, there's two volumes, right? Already showing that there's two volumes there's an initial and a final. There's an initial point and a second point. So I'm going to label left side as initial and then the right side as final. We can already deduce that this is a good point in time where we can say we use the combined gas law. You have two volumes, right? And you have one temperature and you're looking for the other. So let's go ahead and use this. If you look here, the pressure is going to be the same. They're constant. So we don't need P. So I'm going to cross out P. We definitely don't need moles either. It doesn't even talk about moles. It's just saying the gas is either being compressed. So the moles are going to be the same. Only difference is the VI, TI, VF, TF. So with that, we'll go and set up an equation. So VI over TI is equal to VF over TF. And we're looking for this temperature over here. And it must be in Kelvin. So let's make that temperature by itself. In order for that temperature to be by itself, we're going to flip the ratio. So that TI is on top, T final is on top, and the volumes are on the bottom. At this point, we can definitely multiply volume, final, both sides. And then if I were to rewrite this, and then I'm going to cancel these guys out, T final is equal to V final multiplied by T initial divided by VI. So now I can plug in some values in. But before I plug in those values, we know that whenever you're using combined and the ideal gas law, either one of them, you must have the temperature in Kelvin. So let's convert this 27 degrees into Kelvin by adding 273.15. So if you add the two together, then you get 300.15 Kelvin. Now we can put everything in. My V final is 1.80 liters. That's coming from here. Now we have multiplied by T initial, which is our 300.15 Kelvin. All over. We have V initial, which is 2.50 liters. And that would get me my T final. Let's great because liters will cancel. And now we're just left with the unit of Kelvin, and that's what we want. Let's go ahead and grab our calculator. So we have 1.80 multiplied by 300.15. Okay, and I'm going to close the parentheses to let the calculator know that's everything that's on top, divided by 2.50. And hit enter. I get 216. That's the correct sig fix, 216, 216, and the unit is Kelvin. So by utilizing the combined gas law, we were able to get the final new temperature of the gas. In this scenario, it says how many moles of nitrogen gas are present in a 4-liter container. So my volume is 4.00 liter container with the pressure of 0.980 atm and a temperature of 300 K. And it's looking for moles, N. Now here, again, we come up with this a problem. Should we use a combined gas law or ideal gas law? If you set all of the up on the left-hand side, there's volume, there's pressure, and temperature. But you don't have a second volume or a second pressure, second temperature. You don't have another set to compare with. It's not going from one state to another, but it's asking for what is the mole at that state, not going from one place to the next, not from initial to the final. So if you don't see any additional volume, pressure, or temperature, you know that to use the ideal gas law. So let's go ahead and use that, and we want to look for N, the number of moles. So if we have ideal gas law where we have PV equals nRT, we're going to go ahead and divide both sides by RT so that the RT cancels out, and we just have N, pressure, volume, and R and a T. Remember that the R is a gas constant. The value of R is 0.08206 liter dot atm all over mole dot K. That's a little handful, but we're going to go ahead and take all that and plug it into this equation that you have set up. So my pressure is 0.980 atm. Multiply that by the volume, which is 4.00 liters. And it's all over the R value, 0.08206 liter dot atm over mole dot K, and then we have that multiplied by the temperature, which is 300 K. Okay, so we have the 300 K. Let me erase that one. Here we go. So let's go ahead and calculate this out to get the number of moles. Now, we can cancel out all the units. Here's ATM, here's ATM. Liters, liters. Kelvin, Kelvin. And we're just left with moles, and that's good because we're trying to look for moles. Let's go ahead and calculate this out. We have parentheses 0.980 times the 4.00, close it, divided by, and open up another parentheses to indicate we have the R constant, 8206 times the 300, and then close the parentheses. And we get, with the correct sig figs, it's 0.159. 9 moles. By the way, got to add a little period next to the Kelvin. It should be a period there. Okay, so this is how much moles of nitrogen gas, that's N2, are present in this particular state. Now go ahead and try and read the question and see if you could determine which equation to use. Don't necessarily solve it yet. Think about what equation is best fits for this particular equation problem. So if I were to rewrite all of these problem in this format where I could just organize everything together, the volume, temperature, and mass, not moles, but mass is there, and we're looking for pressure. So based on this, there's no two volumes, there's no two pressures or two temperatures. So therefore, we can conclude that we should use the PV equals nRT. So here's my PV equals nRT, and we're looking for pressure. So if we're looking for pressure, we're going to go ahead and divide both sides by volume. And so therefore, this cancels out, and so you have P equals nRT over V. Okay, so you might be wondering, well, I have my temperature, which is there. I have my volume, which is there. R is a constant value, so it's already given, so I'm okay. But we don't have N, the number of moles, right? We don't have number of moles, but we definitely have grams. And we can change that grams of helium into moles of helium by utilizing the molar mass of helium. So every 1 mole of helium, how many grams of helium there? According to the periodic table, there's 4.00 grams of helium. We could cancel out the grams of helium and calculate the moles out here this way. So let's calculate it out. 0.0187 times the 1, right? That's what I'm doing, times the 1. Hit enter, and then divide that by 4.00. That gives me 0.004675. Okay, so I'm going to just go up to 3 sig figs, so 468 moles of helium. Now we pretty much have everything. One more thing, we need to change this into Kelvin by adding 273.15. That will give me 298.15 Kelvin. Okay, now we can plug in everything. Our moles is 0.00468 moles. Multiply the R constant, which is 0.08206 atm dot liter dot mole dot K. And then we have our temperature in Kelvin, that's 298.15 Kelvin, all over the volume, which is 4.11 liters. If you cancel out all the units, you could cancel out the moles, the liters, and get Kelvin. You're left with ATM, and that's good because we want to know the pressure in ATM. So let's go ahead and calculate this out. Putting all of this together, this would be 0.00468 times 0.08206 times 298.15. So all of this multiplied together, hit enter, divided by the 4.11. And that gives me 0.279 ATM. That's my final pressure. So you're going to try the next one, this learning check, and come back and check the key. Here we use the PVnT is equal to PVnT since there's 2 moles. Initial state is 0.100 and it has doubled. So meaning multiply this by 2. The pressure initially is 2.91 and now we're looking for the new pressure with increasing amount of the moles. So I have my setup here and the final answer is 5.82.